This is the Earth Science Classroom. Welcome back to the channel. This video is all on caves and caverns and how they form. This is part of the geomorphology playlist, also the rocks playlist. And this follows on from the chemistry of the caves video and also from the Karst environments video. So this video is going to cover the water movement from the surface, meteoric origins of water in precip as it goes through the karst, limestone, dolostone environment, and how it breaks down the rock, and in stages how it creates the cave. Then you'll look at the different terms and features that these developed caves have with the speleotherms and different terms for each part of the cave, and we'll discuss the fully formed cave and what it basically looks like. So we have our basic karst environment. We have our limestone or our dolostone geology or bedrock, which would be right here with this arrow on the right hand side. Now these kind of like brick type structures and shape and patterns, that's our classic limestone. Now, why is this so important? Because each of these cracks and these horizontal bedding planes are perfect places for water to get down and get through, because limestone is porous and permeable. It will allow water to infiltrate and move through with gravity through the different cracks and fractures and fissures in between the limestone rock in the areas of weakness, and the rainwater will find its way through the rock down deeper through gravity. So we have our precip, okay? And we have our meteoric water, which means it comes from the atmosphere, it comes from the clouds, condensation, evaporation, and we have our falling rain. So what we have in this area right here is our very bare rock, which what karst actually means. It's bare, stony rock. And over here, in this part of the diagram, we have a layer of soil with different horizons, the O horizon, organic, the A, B, all the way through down to obviously the bedrock, which is the limestone. And we also have to the left here, we have some overland flow or surface runoff. Now, why is it not going down, infiltrating through this rock right here? This rock, which is on the top left, this is our impermeable rock. Impermeable means water cannot go through it, so it's non-porous. Porous means there is pores or spaces in the rock that allow the water and gas to move and have some sort of movement. But this is a rock that is impervious, impermeable, and non-porous. So we call this an aquitard. Can't go through. So this could be an igneous rock or a metamorphic rock or maybe a stronger sedimentary rock, but it's not going to be limestone or dolostone. So we have this overland flow. And the same thing here where we have at the bottom, this bottom layer right here, all right, is our aquitard down here, which will stop any further movement down by any water. So you'd have basically this bottom where the water can't go any further. So it's kind of stopped and kept in this part of the rock layers. So we have our water, and we have a little bit of CO2 in the atmosphere, about 419 parts per million currently, which is 0.04%. Okay, so that small amount of CO2 can absorb and combine with the water and fall as rain, and it can fall on the soil or fall straight onto the bare rock, either one, obviously. Now, the soil is important because it includes that humic substances, includes those acids, and includes a lot more CO2. So as the water is going to infiltrate through this thin layer of soil, it's going to pick up more CO2 and become carbonic acid, which is H2CO3. Okay, now this acidic water is going to find its way down through the fissures and the cracks, and maybe dissolve and dissolution this part right here and find its way down, and you see the water making its way down. Now, there is a gradient with hydraulic movement going to the right, so we know this way is towards officially the ocean and lower elevation, so there is going to be a flow of groundwater. So once it hits the ground, or goes into the ground, we call it groundwater, and there'll be a flow of water to the right according to gravity and the elevation and what is downslope. So there are two main terms we're going to discuss for caves in a subterranean environment, and this is phoretic, which means that the cave system it's underwater. Now right here, this line, this dashed line going kind of horizontally across the diagram, this is our water table. The water table shows us the highest extent of groundwater where it is underground. So anything below the water table would be saturated, or a saturated zone. Anything above the water table, anything above this dashed line going up to the surface, would be a zone of aeration, or an unsaturated zone. This is called the vadose. So if a cave system is above the water table and it's just filled with air, then it's called a vadose system, and it's a zone of aeration or a zone of unsaturated zone. So you could have some water in this zone, but it's not fully saturated, not 100% water below the water table. Now the water table can rise and fall according to climate, according to tectonics, according to sea level, and that would create more erosion, more weathering when the water table rises and falls. Has more effect on the cave system and hydraulic action and abrasion. So the water table can fluctuate. So now we added some time, and the elements were working on this karst environment, and it's consistent in terms of the exposure to the carbonic acid with the soil. So here's our soil layer, and here's our soil layer right here with the epicast. Epicast is like the top part, the skin of the karst environment, so to speak, and our bare stony ground over here to the left. We still have the same geology, the same limestone, dolostone, same aquitard, same water table, as you can see. But now, over time, what's happened is you've had this kind of cave system develop because you had the flow of water. Okay, this is traversing through, which means sideways or going horizontal. So you had this vertical shaft here. This could have been a dough line, which also could be over here. Collapsed dough line. Okay, small sinkhole. You could have obviously a sinkhole, or we call it a sink, right here, which connects up to a shaft, and then connects into the cave system. So you have the dissolution and removal of this limestone, dolostone, karst rock, and it's going to flow with the water out this way to the right, as we discussed earlier, with discharge, which can be calculated by Darcy's law if need be. And you have this vertical shaft. This could be a swallow hole, could be a swallette, or could also just be called a sink. This vertical shaft right here, where you have could also be a pothole cave, but that's just the vertical shaft. There's no actual cave system there. So a pothole cave is a similar type. But you have this cave system that on the left-hand side, this one right here with the vertical shaft, is going to be the phoretic cave system, because you're going to have water in the cave right here, because this is all going to be submerged underwater because it's below the water table, whereas this part here is a zone of aeration and it's unsaturated. So you have some dripping down, some water down here, and that would create this underwater cave right here because it's gone down below the water table. Whereas on the right hand side over here with the blue line right here, you have this vadose cave system that is above the water table, therefore it's unsaturated, therefore it does not may contain obviously water because the rain might have some small streams, and both of these would be active caves, okay, or stream way caves, that means that there is water flowing through the caves. Now, obviously, with the ferritic, there's obviously going to be water because under the water table, but with the vadose, there's streams or flow of water through this cave, but you'll have a lot of areas of just air, but could also be wet. You might get some drip water coming through the limestone right here into the cave ceiling, and it's going to drip onto the cave floor and create all those different kinds of speleotherms. And like right here, it could be a stalactite and stalagmite and a column right here. You might have some milk moon, which is like a sidewall kind of flowstone, and obviously the flowstone, which would be like a gypsum, will be on the bottom right here. So these different types of speleotherms and details within this open cave system, or this could be right here, our cavern that's connected to a lateral tunnel. And inside here, in the actual cavern, you'd see a lot of the evaporites, the precipitation minerals left, creating these features. And if you look at the ferritic cave system right here that goes below the water table, you'll see that it ends right here currently. But what's going to happen is, because this is an aquitard and impervious layer of rock, and it's a metamorphic rock, you're going to have the development and movement of the cave going this way to the right along the impervious layer, creating more and more dissolution right here and flowing towards a downward elevation towards the ocean. So in time, this cave would develop as far as the limestone, dolostone geology exists, or where it meets the ocean. So it's a great example of both the geology and the rock types linking up with weather and erosion and climate and the environment and elements, and how they create this beautiful cave system with different shafts, different types of sinkholes, disappearing streams that would be forming these lovely tunnels and cave systems, both vadose above the water table and below, which is called ferritic, and all the great features that we see in these caves and caverns between all the speleotherms and evaporites. And it's just fantastic. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.